My name is Jovan Menezes, and I'm a second-year PhD student here at Cornell University in robotics. And today I would like to talk about the work that we presented at ICRA, which is a semantic and occlusion aware Gaussian mixture probability hypothesis density filter. So, yeah. Getting into it, in this work, the problem that we are tackling is multi-object tracking. And in this task, the goal is to estimate the number of objects, their state, and the trajectories of these multiple dynamic objects in real time using noisy sensors as an autonomous vehicle or a robot moves around in the environment. So as you can see on the right over here, it's like a car. It's the LiDAR image of a car. It's the LiDAR video of a car moving around in the scene. You can see the tracks. And the reason we use tracking instead of standard frame-based object detection is because it gives a high-level reasoning to our agent. It helps us reason about things like occlusion and outliers instead of just using frame-by-frame object detection. And as I mentioned, the multi-object tracking sees application in a number of areas: autonomous driving, mobile robots, air traffic control, and so on. So broadly at a high level, there are two classes of methods that are used in multi-object tracking. One being tracking by detection. And as the name suggests, this is like a decoupled approach where we first perform object detection and then we use either Bayesian frameworks or learning-based methods to perform tracking using these detections. So it's essentially a sequential process. And there are a lot of methods that have been developed in literature, like BiTrack, DeepSort, and AB3D-MOT. The advantage of this framework is that it's modular in design, and you can simply leverage powerful, or as object detectors keep improving, you can leverage these object detectors without necessarily needing to update or train the downstream tracking algorithm. And also, this makes it very flexible to integrate different tracking algorithms with different object detection frameworks. The drawback of this is that it's computationally redundant. There is a lot of computational redundancy, and a lot of these methods don't explicitly use contextual reasoning. On the other hand, the other class of methods is joint detection and tracking. And as the name suggests, we perform object detection and tracking in a single framework. And examples of this include TrackFormer, CenterTrack, and FairMOD. As I mentioned, the advantage of this framework is using end-to-end optimization, and it eliminates duplicating backbone for the object detection and tracking framework. And the cons are you need large-scale training data since we are doing this end-to-end, and a lot of times it tends to generalize poorly, and as mentioned, and as we know, like since it's end-to-end learning-based framework, there is limited uncertainty modeling. So the method that I'll be presenting today is from the tracking by detection framework. The reason being, like tracking by detection is more preferred for safety-critical applications such as autonomous driving. So what are some of the current challenges that we face in multi-object tracking? So one class comes from environment and motion ambiguities. And this primarily comes from objects, from the objects in the scene or the scene itself. So we have objects like pedestrians or cars moving dynamically in the environment with unpredictable trajectories. We have frequent occlusions, such as pedestrians going behind cars or larger objects, and target birth and death, which is how do we understand that object has essentially left the sensor field of view or the scene, or is just entered new. The other class comes from hardware and data association bottlenecks. So one of the main challenges in tracking is data association, wherein we need to understand which detection that we get at the current time step right now associates to which track that we have been object which we have been tracking so far. So this is generally a NP-hard combinatorial assignment, and it also becomes difficult because we have imperfect sensor. So LiDAR, camera, they tend to have, particularly LiDAR sensors tend to have a lot of noise and interference, and a lot of these sensors even tend to degrade with adverse weather changes. Also, one of the challenges is real-time latency. So we need a lot of these algorithms to run in real time, given the application. So to tackle these challenges, in this work, we present a semantic and occlusion aware Gaussian mixture probability hypothesis density filter, wherein we integrate occlusion reasoning and scene semantics to generate birth hypotheses in a Bayesian framework. We observe that we see that this integration helps to improve computational efficiency because we are concentrating birth hypotheses in regions where we expect new targets to emerge or new targets to enter into the scene. And this also improves robustness to sensor noise, clutter, and frequent occlusions. We also evaluate our method against multiple baselines using Monte Carlo simulations and on the real-world kitty data set. And finally, all of this proves that we can achieve improved tracking performance while also lowering track initialization delay and reduced cardinality error and different other metrics, improvement on different other metrics that are commonly used to evaluate multi-object tracking. So to get a little bit into the method, the whole frame, the method that I'll be talking about comes from a framework called random finite set, RFS for short. And RFS provides a unified Bayesian framework for multi-target state estimation. It essentially allows us to formulate the entire tracking problem probabilistically, where all aspects of the problem, such as unknown number of targets, the target state, sensor measurement, clutter, and misdetections, can all be modeled in an elegant probabilistic manner. It essentially extends the traditional Bayesian filtering framework from single object to multi-object tracking. And at the core of it, how it works is we represent the states as seen over here with X, and the measurements that we get from our sensors, represented by Z, as sets. So capital XK represents the set, and each element in that set is essentially a target. And similarly, even on the measurements, each measurement is represented by small z. And in this framework, both the number of measurements (mk) and the number of states (nk) are varying over time. And a couple of key RFS filter implementations include the probability hypothesis density filter, which we have used in this work. There's the cardinality PhD filter, and different Bernoulli filters, labeled and unlabeled. So we'll be focusing on the first method over here, which is the probability hypothesis density filter. So how the PhD filter essentially works is in RFS, we have the state XK shown over here, which is a combination of, which is a set combined of two sets, two subsets. One is XK, which represents the targets that have survived from the previous time step, and the set gamma K, which represents new targets which have just entered into the scene. So in the PhD filter, what we essentially do is we take the first order moment, which is called the intensity or the PhD of the state xk, which is represented by nu k over here, and nu k essentially represents the state, the intensity of the set xk. Similarly, for each of the subsets, we have the corresponding two intensities. And at the bottom, we see how the PhD filter essentially works. And we can see a lot of similarity with single object tracking algorithms, single object tracking methods. So we have the prediction step wherein we use a transition model to propagate the state of objects from the previous time step to the current time step. And we have new target birth or track initialization or birth hypotheses, the intensity represented by gamma k. We essentially combine them and we perform soft data association instead of explicit hard data association, which is commonly done in a lot of methods. And we also at the same time update the state. So using, again, the transition model or the state dynamics, we can simply update the state to the current time step. And over here, we use the measurement to perform the update step. And this intensity is, again, used recursively as similar to how we do in single object Bayesian framework. To extract the state of each object from the intensity, we perform some post-processing steps such as pruning, merging, and this finally gives us the state estimation or the multi-target state estimation at the current time step xk. So in our work, the intensity is represented by a combination of weighted Gaussian mixtures, as seen over here. So we represent the intensity, the predicted intensity over here, nu k, given k minus 1, which is the predicted intensity by a combination of weighted Gaussian mixtures, where W represents the weight of each component, and the mean and the covariance is represented by M and P, respectively. So essentially over here, we are using a combination of multiple Gaussian components to sort of represent the intensity, the predicted intensity. And within this predicted intensity, we also model the new target hypothesis or the birth hypothesis represented by gamma k. And over here, we also represent this birth intensity using a combination or multiple Gaussian or a Gaussian mixture model with the weights represented by W gamma and the corresponding mean and covariance. So intuitively, what this means is like each component defines a potential location or state where a new target may appear into the sensor field of view or into the scene. And the design of the birth model is critical because this is where we actually start tracking objects, and we want to reduce the delay between receiving a measurement and actually starting to track a target in applications such as autonomous driving. You don't want too much of a delay between receiving a measurement and actually starting to track an object. And the birth model essentially influences the entire PhD filter pipeline. So in this work, what we do is we leverage semantic reasoning, scene semantics and occlusion reasoning, and we embed that into the birth hypotheses of the Gaussian mixture PhD filter. And how we do that is using three sets of terms. So at the top, we see the combined birth intensity, represented by gamma k. And this gamma k consists of three terms. First is the occlusion term on the left, represented by gamma occlusion. So these are the birth hypotheses which we define using occlusion reasoning. In the middle, we see the birth intensities, the birth hypotheses, which we define using scene semantics. And on the right, we see the objects, we see the birth intensity represented for the sensor field of view. So the one on the left, the occlusion term is for occlusion reasoning, which helps us to prioritize regions where we expect objects to enter the scene of the scene or the sensor field of view given based on the occlusions. The center term is for semantics, wherein we leverage deep learning-based semantic models to provide us regions in the sensor field of view where we expect new targets to enter the sensor field of view. And on the right is the sensor boundary. So this essentially accounts for targets which we would expect to enter the sensor field of view from the outside. Visually, what that means is if we have a scenario, as we see on the right, where we have an ego vehicle represented in dark blue in the center, and we have an object, an occluding object, we can define these occlusion cones, which help us understand which areas in the sensor field of view are prone to objects entering the view from occluded areas, and we define the occlusion based birth hypotheses along the boundaries of the occlusion cone. Likewise, we using deep learning semantics, we define regions represented in pink over here where we expect new targets to emerge. So, for example, for pedestrians, that would typically mean sidewalks. Pedestrians entering the sensor field of view from buildings would be on sidewalks and not in the middle of the road. So we define both hypotheses along these semantic regions as seen in green, and finally we define the both hypotheses along the sensor field of view, along the boundary of the sensor field of view, which accounts for objects just entering from the outside of the sensor. So then we simply combine each of these birth hypotheses by adding each of these components by adding them together. And similarly, the weights also are the combined weight of the birth intensity gamma is a simple summation of all the of each component of the weights of each component arising from each birth hypothesis, and how we determine the weight of each component is seen over here at the bottom. So nk hat represents the expected number of new targets, the expected number of new targets that we believe would enter the sensor field of view at a current time step. Rho is a weighting factor that we use to weigh each source. For example, if for some application we would want to weigh occlusion terms more than semantic terms, or vice versa. So rho is a weighting factor, and by simply normalizing them, we get the weight of each component in the birth hypothesis, so the birth model of the PhD filter. Next, we evaluate our setup using simulation first. So we have a dynamic simulation environment, as we see on the left. We have an ego vehicle moving in an environment. We have static and dynamic obstacles, such as cars, and large obstacles, such as buildings. And we have, in this case, we have 6 pedestrians moving about randomly in the environment. And to compare our approach, we use multiple baseline approaches. So one is standard Gaussian mixture PhD filter, wherein we need a priori information to define the both hypotheses. And as expected, this may not always be available for a dynamic application such as autonomous driving. Then we have the uniform PhD filter, where we just uniformly distribute the birth hypothesis over the entire sensor field of view. This is extremely computationally inefficient and can result in a lot of missed tracks. Then we have the partially uniform, which is a downsampled version of the uniform PhD filter, wherein for the observable states, we uniformly distribute the birth hypotheses, and for the unobservable states, such as velocity or heading, we may use a priori information. Again, over here, we have a lot of unnecessary components, birth components, which can result in a lot of delays and reduce tracking performance. Finally, we have the adaptive target PhD filter, wherein we just assume all measurements that we receive are true, and we start tracking them. And this can be very dangerous for a safety critical application like autonomous driving. And for each of these methods, we also implement a PhD variant from literature, wherein we can jointly estimate the probability of detection and probability of survival. These are parameters or hyperparameters that we provide to the filter. And in this variant, we can jointly estimate these parameters as well. So Over here, we show the results of our semantic and occlusion aware Gaussian mixture PhD filter. And on the left, we can see the simulation environment, and on the right, we can see how the intensity of the PhD evolves over time. And this is one of the great advantages of using a framework such as RFS. So instead of simply running a Kalman filter or some other Bayesian tracking framework for each target, we are able to receive sort of a combined multi-target posterior density. So this is one of the reasons why RFS filters are really good for multi-object tracking. Quantitatively, we evaluate our approach against all of the baselines. First, by using track initialization latency, wherein we evaluate how much time it takes for each method to start tracking a target after it receives a measurement or a detection. And we see that our method performs better than the strongest baseline in 72% of the cases. Again, that is the partial uniform. And in all of the cases for the uniform and the standard GM-PhD. Against the adaptive, it performs better only in 5% of the cases. And like I said, that's because adaptive model um, just starts tracking targets as you receive each measurement. And this doesn't consider false positives or noisy measurements. So that's why we see the adaptive target performs well over here. Similarly, we evaluate against the other set of methods wherein we, as I mentioned, we are able to dynamically evaluate the probabilities, the hyperparameters that we define in the PhD filter. And again, over here, we see a similar trend where our method performs strongly as compared to the baseline approaches. Next, we evaluated our method against the adaptive target PhD filter, specifically with varying noisy measurements, with increase in noisy measurements, to understand how robust is our method as compared to the adaptive with the adaptive target PhD filter. And we see over here that even as the noise parameter lambda increases, our method still has higher precision. It doesn't start tracking false positive or noisy measurements. On the other hand, the performance of the adaptive target PhD filter decreases drastically as the noise in the sensor increases. We also evaluate our method using the mean absolute cardinality error, wherein we evaluate the number of targets that are being tracked at each time step, as well as the OSPA, optimal subpattern assignment metrics, which are commonly used to evaluate tracking algorithms from RFS framework. And again, over here, we see when we plot the mean and the standard deviation for each metric for all the baselines, we see how our method gives better performance as compared to the other baseline approaches. Next, we also evaluate our method on the kitty data set. So over here, we use the entire kitty data set validation data set, and we perform centfold cross validation. And here we use 3D object. We use the LiDAR point cloud to perform 3D object detection and semantic segmentation. And again, we see similar results where our method, compared to the partial uniform and the uniform PhD filter, has better cardinality error as well as the OSPA metric. And on the right, we see how our method, even on the kitty data set, reduces the track initialization delay as compared to the baseline approaches here. So it's essentially our approach reduces the latency and track initialization while improving the cardinality error and the OSPA metric on the kitty data set as well. We also evaluate the computational performance of our method against the baseline approaches. And here we see how our method, and we evaluate that based on the number of Gaussian components in the posterior intensity of the filter. And here we see how our method has lower number of components as expected than the two baseline approaches. So this helps to improve real-time performance, which is required for a lot of applications. We also evaluate our method for sensitivity to different parameters or sensitivity to parameter tuning. And essentially here we evaluate how we define the number of the expected number of targets at each time step, because this might not be available in all scenarios. So we basically vary the expected number of targets from the ground truth that we get from the Kitty data set. We vary this parameter, and we observe that even with variation in this parameter, our method still reduces the latency and track initialization as compared to the baseline approaches. So to sum up, in this work, we proposed a semantic and occlusion aware Gaussian mixture PhD filter, wherein we integrated scene semantics and occlusion awareness in a Bayesian tracking framework. This method allows us to initialize birth hypotheses in likely emergence areas such as occlusion boundaries, semantic regions, and the sensor field of view instead of uniformly distributing the hypothesis over the entire sensor field of view. It allows us to it allows us to start tracking targets or objects sooner, and it is also robust to false positives. We conducted experiments on a real-world data set and on simulation in Monte Carlo simulations, and we compared our method against multiple baseline approaches and showed better performance. And finally, we evaluated our method for sensitivity to parameter tuning and computational efficiency. And all of this helps us prove that our method can be used for real-time deployment. And with that, I thank you for your attention and happy to take any questions.